Okay, what we're going to look at right now is the vicinal addition of a halogen to a double bond. So first off, we need to have an alkene. And I am going to use cis-2-butene. And you would do this reaction with either bromine or with chlorine. And when you do this, make sure you are using a solvent that is not capable of being a potential nucleophile. So I usually use something like chloroform here or methylene chloride, something along those lines. Now, because this reaction occurs with anti-addition along the double bond, I like to draw on the stereochemistry of the other groups so that I don't have to worry about that during the course of the reaction. Okay? Now, as this reaction occurs, you initially have your alkene in solution with your halogen. Now, this is the reaction I call the tent reaction, okay? So if you can't remember, that's what I kind of have talked about it as in class. Now, usually your diatomics are highly stable and non-reactive, but in this case they will react with the double bond. The double bond is going to act as a source of electrons. It's the electron pair donor, and it will donate them to one of these two bromines. It doesn't matter which one. And as that occurs, since bromine only wants to have 8 electrons, the bromine-bromine bond will break, and the other bromine gets both electrons. There is not going to be a carbocation formed, so the bromine also donates an electron density back into the carbon system. As you do this, you make what I call the tent. It's called the cyclic halonium ion, but I call it the tent because it looks like a tent to me. So there's the tent part, and I'm now putting in my little stakes. If you remember, we had the stakes of the tent in the ground. Okay. And we have a bromide left over from the previous step. Now, I know this is not a carbocation. It's not. But that positive charge on bromine is delocalized over the bromine in both of those two carbons in this 3-membered ring. If you think about the carbon-bromine bond, by induction, the electrons are being pulled toward the bromine. So these carbons in this 3-membered ring do experience some of this positive character. Now, depending on how and what kind of an alkene you have, the positive charge tends to reside best on the more substituted carbons. So if you were dealing with a tertiary carbon and a secondary carbon in this 3-membered ring, the positive character would reside more on the tertiary carbon than it would on the secondary carbon, and that will allow you to result in major and minor products. In this case, they're both secondary carbons, so they both probably have very similar amounts of positive character. What happens is, with our camping trip, is we have a little mole in the works. It's bromide. He's going to act as our nucleophile. He's the electron pair donor, and he will donate the electrons to one of these two carbons here. This is actually an SN2 substitution because we end up doing a backside attack and having a leaving group depart. But if you do have unequally substituted carbons, the bromide would be more likely to add to the more substituted carbon. That would be the one that would result in the major product. In this case, it won't matter. You can add it to either one. But it does do this backside attack, so it crawls underneath the tent to ruin your camping trip. And as that happens, your tent pops open because the carbon-bromine bond is polarized toward the bromine. Bromine gets those electrons. Once this has occurred, you can see how we get this anti-addition of bromine along the double bond. And if you've drawn in the stereochemistry of your groups initially from the double bond, you don't have to worry about what was a wedge and what was a dash. They're already set in stone for you. But be aware, again, you may have some major and minor products if you started out with carbons along the double bond that were secondary and tertiary, or secondary and primary, or primary and tertiary. This is the product we would result with in this case, plus its enantiomer.